So consider yet again our basic circuit where we've taken a collection of linear time invariant circuits or devices that may be very complex and sophisticated, and replace them with an equivalent circuit. If they deliver energy, then we can replace it with the Thevenin's equivalent. Connected to that is a sequence then of very sophisticated linear time invariant electrical engineering, which we likewise have replaced with an equivalent circuit. And since they're linear time invariant, that equivalent circuit is simply an impedance, the input impedance of everything to the right of this plane, and that becomes the load impedance then for this source. And we've shown with these equivalent circuits we can correctly determine the current and voltage at this port plane, and of course from that determine the power, the rate of energy flow from one side to the other. Now we can change this slightly here and talk about the voltage right here as the voltage right here as being the output voltage from the source, and the voltage just on the other side of the port plane as being the input voltage to the load. Likewise, we can talk about the current just before the port plane coming out of the source as the output current from the source, and likewise the current at just the other side of the port plane being the input current to the load. Now this seems like sort of redundancy here. We know from KCL and KVL that the input voltage is equal to the output voltage, and likewise the input current is equal to the output current. So why did we separate the voltage and current in the port plane into these two components when they're quite evidently equal to each other? Well, let's say some annoyed mechanical engineer comes along and says that we can't directly connect our devices to each other. We have to displace the source of the load by some physical distance. There's some reason in terms of balance or mass or mechanical design why this needs to be. So what do we do in this case? It seems like we could just go to the lab and find some wire, some conducting wire, and get our soldering iron and go through and connect wires from the output of the source and connect them then to the input of the load. How long do these wires need to be? Well, they depend on the displacement between the source and the load, the distance between them. This might be, who knows, several meters, or it could be just a few centimeters. Either way, we can simply connect the two devices with these wires. But there's a potential problem with this solution. We might turn on our source and begin to measure voltages and currents, and we measure the output voltage from the source and we measure the input voltage to the load, but we find that those two voltages are not equal to each other. Now, of course, we're assuming time harmonic sources here, so they have the same sinusoid with the same frequency. What we're saying is that the magnitude of the output and input voltages will be different from each other, and their relative phases will be different. They may be out of phase by some amount. Similarly with the current, we measure the current coming out of the source and we compare it to the current into the load, and we find that those two currents are not equal to each other. They have different complex representations, different magnitudes and phase of their oscillations. So what do we make of this? Kirchhoffs laws, we think, KCL and KVL, should tell us that the current either end of the wire should be the same and the voltage either end of the wire should be the same. So why are we measuring something different? Well, the problem is not with Kirchhoff and his Professor Kirchhoff and his laws. The problem is how we view the wires, how we view these devices, and how we think they behave electromagnetically. In fact, the behavior of these wires are more complex and more difficult than we might have imagined back in our freshman circuits courses. Of course, if we assume that there's no voltage drop across the wire, we have current flowing through it, but that results in no voltage from one end to the other of that wire. Then, same thing for the bottom wire, then we can do KVL, and we would find that V out and V in are equal to each other if we assume that there's no voltage drop, voltage change across this wire. Similarly, even though there is a voltage difference between the two wires, we assume that there will be no current flowing between these two wires. And if there's no current flowing from one wire, the top wire, to the bottom wire, then by KCL, we would find in that case that the output current from the source would be equal to the input current, the load, if, again, the current between the two wires were equal to 0. If we assume that's true, then we get an equality with respect to input and output current. Now, you may say, we assume that there's no current between the wires, and we assume there is no voltage drop. Should we say that that's true, or don't we know that that's true without question? Well, it turns out that that's true without question only if the currents and voltages are DC. And that's really only true if we assume we have perfect conducting in the wires and a perfect insulator that separates them. That's generally the case that we assume in our circuit analysis. And so again, seems like we should be able to say the current in and out are equal and the voltage in or out are equal if we have good conductors and good insulators. But once again, we can only say that if the currents are strictly speaking and voltages are strictly speaking DC, if omega is equal to 0. But of course, in this class, we are talking about not only sinusoids, but because of radio frequencies, very high frequency sinusoids. And so we're not only not considering DC currents and voltages, we're considering DC currents and voltages that are very different, very high frequencies compared to a frequency of 0. So here is the current into our wire, written as a real value current with respect to time. And of course, that is the physical truth of the current. It is a real value, and it is changing with time in a sinusoidal fashion. That's what we're assuming for everything in this class. And of course, the complex representation can be converted into the true physical reality of the current by taking the magnitude of that complex number, which gives us the magnitude of the oscillation, and the phase of that complex number, which gives us the relative phase of that sinusoidal oscillation. So I wrote it this way so you can see that we clearly have a current now that is time varying. It's not DC. And of course, you remember what happens when we have a time-varying current. The physics associated with a time-varying current, specifically the physics associated with that of discovered or published by Michael Faraday. You recall from your electromagnetics course that anytime you have a current that flows, there is a magnetic field, a magnetic flux density that is created, a solenoidal field that's created by a flowing current. Now, if that current is time varying, then the B field, the magnetic flux density, will likewise be a time varying field. And Faraday showed that anytime you have a time varying magnetic field, magnetic flux density, it induces an electric field. And the equation that relates Faraday's law in Maxwell's equation is written here. The curl of the electric field is equal to the time varying, the time derivative rather, of the B field. And so if we have a B field, magnetic flux density rather, that's changing with respect to time, what we'll find is the electric field that results must be non-zero. We have an induced electric field. And so if we take an electric field and we integrate that electric field along some path, what we find when we do that integration is we can show then the voltage between 2 points. Now, in the case of this induced electric field that's created by a time-varying B field, you'll recall it is a solenoidal field, and therefore the value of voltage that we measure depends on the path of integration. And if we took the path of integration along the conducting wire, if it were perfect conducting, we would, in that case, get 0. But generally speaking, we go through and define the voltage measured by this induced electric field by taking a path that extends outward from the wire and back then to another point. And with this general sort of out from the circuit and back integration path, what we'll find is the voltage measured will be non-zero. The time-varying current creates a time-varying magnetic flux density, which induces a time-varying electric field, which then we can measure a voltage then between 2 points, in this case 2 points which are at one end of the wire and the other. We have an induced voltage. Well, this behavior sounds very much like an inductor, doesn't it? We have a time-varying current then which creates a time-varying voltage across an inductor. And this inductor, of course, is simply a circuit element realization of Faraday's law. We design a device that enhances the induced electric field and thus the resulting voltage. And of course, the proportion between the resulting induced voltage and the time-varying current is a value which is the inductance of that inductor. If we have sinusoidal time-varying currents and voltages, we can write them in terms of their corresponding complex voltage and current in this form. And we can see then that the magnitude of the oscillating voltage and current is simply related to by a value of omega L, and the relative phase between the oscillating current and voltage, the sinusoidal current and voltage, that relative phase is a difference of pi over 2 or 90 degrees between the two. So am I saying that a wire is actually an inductor? Well, actually I am saying that. Any length of wire will have a certain inductance and will induce an electric field, and therefore we can measure a voltage between one end of the wire and the other. The voltage at either end is not the same as we've sort of assumed up until this point. The best way to model wires then is not as a lumped inductor, but sort of a series sequence of very small inductors. We can think of a chain of very small inductors kind of all soldered together. And of course that means that the longer the wire is, the more total inductance we have between one point and the other, and therefore perhaps the larger the induced voltage between one point and the other. Certainly, if we look at the circuit model in this way, look at it as an equivalent circuit. Instead of seeing a wire, we see a series of inductors. Hopefully it become evident to us that when we apply KVL, that we no longer can assume that the input voltage to the load would be the same as the output voltage from the source. And the reason is because we have these voltage drops across the inductors that form the wire that we are analyzing. Now, this may be news to you. This may be something that you've never heard of or considered before. Certainly in all your circuits classes, wires were very simple devices. The current at one end was equal to the current at the other, and the voltage at one end was equal to the voltage at the other. Why now all this complication involving inductors, and why weren't we discussing it your freshman year? Well, the reason is that for many cases, the induced voltage that results is very small. And so therefore, even though theoretically the voltage at the input of the load would be different than the voltage at the output of the source, it would not be appreciably different. The voltage drops due to these inductors, this induced electric fields, are so small that they would be difficult to measure, or from a calculation standpoint, they would be down in digits that were insignificant. And so we simply approximate them as zero. And of course, that makes our analysis much simpler when we do so. And that's what you've been doing for most of your low frequency circuit analysis. So when do we know when we can neglect these induced voltages? When can we decide that they are insignificant? Well, we can sort of look at the voltage, the magnitude of the voltage across an inductor, and make that decision. Again, what we're really saying is, when is this voltage, this induced voltage, so small that we can consider to be zero? Well, we look at the result here, and you can see that it is the product of three different terms. And what we find is, if each of these three terms are small, even though they're non-zero, if each of them are small, when we multiply them together, we'll get a small number. And of course, once we start multiplying small numbers together, the result becomes even smaller still. So let's look at these three values. The first one is L, that we'll look at, the inductance of the wire. How much inductance is in a wire? Well, it depends on the length of the wire. The inductance of a wire is proportional to its length, assuming that the wire cross-section is the same at every point. If we double the length of the wire, then we are doubling the total inductance of that wire. So the first thing that we think about when it comes to do we need to consider the induced voltage is how long are our wires? How big is our circuit? So in most cases, the length of our wires are relatively short from the standpoint of creating much inductance. The exception is we have transmission systems. And so transmission systems, let's say like power transmission systems, the lines, the wires could be, of course, tens of kilometers, hundreds of kilometers, even thousands of kilometers long. And so we're talking very long wires, very large inductance. We can also have communication systems where we have cables that are long, although many of those cables are being replaced or almost exclusively replaced now with fiber. In addition to the length of the wire corresponding to inductance, we also, when we look at this, have to consider the magnitude of the current. How much current is flowing through those wires? Again, from the standpoint of power transmission, the current can be very significant. And so with respect to power transmission, we could have a large amount of current and a large amount of inductance. Now, omega for power transmission, of course, is relatively small. 60 hertz times 2 pi, that's a small number, but it's not zero. And so what we find is the induced voltage, when we're talking about power transmission, can be, is a big problem, something that we have to consider mathematically when we analyze those systems because of the relatively high current and certainly large inductance associated with transmission line cables. I say the current, never mind. What about the third term in this product, the product of three things, and that would be omega, the frequency, 2 pi times the frequency of the oscillation in hertz. And for much of what we do in electrical engineering, and certainly back when I was in school a long time ago, the frequencies we dealt with were relatively low frequencies. If we talked about an audio system, they would be in the kilohertz. Even in some communication systems, radio, they would be in the hundreds of kilohertz or tens or hundreds of megahertz. They're relatively small, low frequencies for omega. We can then conclude that these induced voltages, due to the inductance of the wires, can be neglected as small and therefore insignificant if the circuit is small. In other words, the wires are short and the inductance is low. If the power is relatively low, the current is not significant. High power kinds of application, and the source frequency is relatively low. If all three of these values are small and we multiply them together, again, we're going to get a small value, and therefore we can conclude that the input voltage at one end of the wire is going to be the same as the output voltage at the other. But if any one of these three is not small, then we cannot ignore the induced voltage. So we have a situation where one of the three is not small, the other two are non-zero. Again, we're going to have then a bit of a problem. So one condition where one of those three values are not small is when we are talking about radio engineering, microwave engineering. In those cases, omega is much greater than 100 megahertz, hundreds of megahertz, gigahertz, tens of gigahertz, even into 100 gigahertz. So we're looking at millions and billions of cycles per second. And in that case, even though our wires are relatively short, our inductance are relatively small, and the current through them is relatively small, because omega is so large, the induced voltage cannot be ignored. In fact, they can be very significant, such that the voltage at one end of our wire may be very much different than the voltage at the other. And so extremely large frequencies cause us to have to consider these induced voltages, and we no longer can view our wires the way we did in the happy days of our freshman year, when voltage at one end was the same as the voltage at the other. Now let's consider current. Of course, we've always thought that the current coming into the wire must be equal to the current coming out of the wire. But once again, that's not necessarily true. We found that these will be equal if there are no current flowing from one wire to the other, but essentially there is in our system, and that is because the two wires themselves form a capacitor between them. There is a capacitance between one conductor and the other. And because there is a capacitor, we can have displacement current flowing from one wire to the next. Now, displacement current physically really is just charge piling up at different points in the wire for different values. But we model this phenomenon as a displacement current flowing through a capacitor, really charge again piling up on the capacitor plates, which physically in this case would be our two wires. The result, though, is that the current at one end will not be equal to the current of the other. And again, the reason is the capacitance that we have between our two wires. So we can ask ourselves then, when is this displacement current significant? When do we need to worry about this displacement current? We can go through and look at the equation for the current through a capacitor relative to the voltage across it, and we come up with this result for complex currents and voltages. Of course, hopefully this is well known to you. We can take the magnitude of this result and see that the magnitude of the displacement current is equal to the product of the frequency of oscillation, the capacitance of the wires, and then the magnitude of the voltage between the two wires. So when is this going to be significant? Well, it's when any one or more of these is significant. Let's look at the first thing we'll look at is the capacitance between the two wires. Just like inductance, the capacitance between the wires are proportional to the length. The longer the wires, the larger the capacitance. So just like we had for inductance, the displacement current can be significant when our wires are very long. And once again, this can be a problem for transmission systems like power transmission. In addition, for power transmission, the voltages are extremely large. So when it comes to displacement current, we have two of the three things that we know are going to be very significant. If we have long transmission systems, the capacitance is going to be large. Certainly the magnitude of the voltage is going to be very large. Once again, omega is not too bad, 2 pi times 60, but since two of the three are very large, we are going to have displacement current that has to be dealt with in power transmission systems to accurately model their behavior. We can't simply say that the current at one end of our transmission line, power transmission line, is going to be equal to the current at the other end. That's certainly not going to be the case. And the third term in this product is omega. We talked about this before. For inductors, for many electroengineering system, omega is not particularly large. We're talking about audio-video systems. Again, your first year in school, when you're doing your circuits class, you're dealing with frequencies that are relatively small. Your wires were relatively short. They fit on the lab bench in front of you. And of course, we don't trust you with very high voltages. So the voltages were likewise relatively low. And so we didn't have to worry about displacement current, and it wasn't part of your calculation. You just assumed naively, but assumed that the current at one end of your wire would be equal to the current at the other. And anytime you have a time varying current or voltage, a sinusoidal voltage, this assumption is only approximately true at best. So in summary, again, if your wires are short, your voltage is low, and your frequency is relatively low, then the displacement current that results is not significant, and almost certainly you can ignore it in your analysis. So in radio engineering, of course, our frequencies omega, or our cycles per second, are in the hundreds of megahertz into the gigahertz, tens of gigahertz, or even 100 gigahertz. So we're talking about very high frequencies. And so even though our circuits are small, maybe very small, I mean, the wires may be length of just a few centimeters, but at these high frequencies, their inductance capacitance are large enough that the resulting induced voltages and displacement currents are going to be significant, and we have to account for them. So in this class and all high frequency, radio frequency kinds of applications, when we see wires, we don't see these nice conductors where everything is the same on either end. Instead, we see wires, we see inductors, capacitors. We see two wires connecting our source to our load, and what we really see is a two-port network that's filled in the inside with reactive elements, series inductors and shunt capacitors. And because of that, we have many induced voltages and we have much displacement current. And so we have to count for this circuit model when we do our circuit analysis. The key thing here is we can no longer go through and assume that the current into our load is the same as the current out of our source, and likewise the voltage across our load is the same as the voltage across our source when the source and the load are not directly connected. Instead, they are connected by wires, conductors. So this makes things quite a bit more complicated, of course, in terms of trying to get our radio systems to work. Again, our wires are big hunks of reactive networks, and so how do we deal with that? You might say, how do we get rid of the induced voltages and displacement currents? Well, we can't get rid of them. They are there. All we can do is try to design our systems in a way that they are more easily dealt with in terms of our designs and our mathematical analysis. And so there are some things we can do to make this a bit easier. So our solution to at least mitigate these problems, if we can't eliminate them, is to build our wires in a very rigorous fashion in terms of its manufacturing. We want their characteristics to be repeatable, predictable, and unalterable. We want to design our pairs of wires such that they are continuous with respect to their structure. In other words, if I took a pair of wires connecting a source and a load and I were to slice it through in any point and look at the result, I would find that the cross-section would be exactly the same. And so examples of this are coaxial lines that you may be aware of and we'll talk about. The relationship between the two conductors are very precise. Each one is a cylinder, one cylinder inside the other. The radius of each cylinder is specified. The dielectric between them is specified. We have a few parameters that parameterize the wires specifically in a way that allows us to predict their inductance and their capacitance. And that's the key thing, that we want to be able to design them to give it certain values of L and C such that we can use those in our analysis and design of our further circuits. So these structures that we build, these two wires that we build that are repeatable, predictable, and unalterable, are a structure that we call transmission lines. And again, coax is one of probably the prevalent transmission lines that we use, but there are other ones that we will talk about. So again, there's no getting around the fact that we induce voltages and we likewise induce currents, diffusion currents, displacement currents rather. But if we have transmission lines, at least we can do the analysis in a somewhat reasonable and tractable mathematical way.